Hey everyone, and welcome. Today, we're going to crack open the recipe book of modern medicine to tackle a really big question. How are vaccines actually made? We're going to dive deep, way beyond the headlines, and step into the high-tech kitchens where these life-saving medicines get cooked up.
I mean, you've probably wondered, right? It seems kind of like magic, how something goes from a scientist's idea to a little vial in a doctor's office. But it's not magic. It's this incredible story of precision, where biology and engineering come together. And we're going to break that whole journey down for you, step by step. Okay, so before we jump into the kitchen, let's get on the same page. What even is a vaccine? Well, the best way to think about it is like a fire drill for your immune system. It shows your body a safe, harmless piece of a pathogen so it can build a memory of it. That way, if the real bad guy ever shows up, your immune system is already trained and ready to go. You get all the training without any of the actual danger. Pretty clever, right? Now, you might be thinking, hold on, there are tons of different kinds of vaccines out there. And you're absolutely right. But here's the really cool part. Almost all of them, from the old school classics to the cutting edge new stuff, are built using the same fundamental blueprint. So let's check out that master recipe first. Just picture the whole thing like a super clean, super high-tech, three-stage industrial kitchen. No matter what kind of vaccine it is, every single one has to go through these three main stages to get made. And here is that blueprint. It's pretty straightforward. First up is the upstream process. This is where you grow the key ingredient, the thing your immune system needs to see. It's called the antigen. Next, you move to the downstream process. This is all about purification, cleaning up that antigen with incredible precision, getting rid of absolutely everything else. And finally, you have formulation. That's where you mix the pure antigen with a few other key ingredients and package the final product. Grow, purify, package. See? Every vaccine follows these basic rules. All right, let's start with the oldest recipes in the book. The original strategy was actually brilliantly simple. Just use the entire pathogen itself. Yep, the idea was to show your immune system the complete enemy, the whole shebang, but only after making absolutely sure it couldn't cause any real harm. And they did this in two main ways. On the one hand, you've got live-attenuated vaccines. This is where scientists basically tame the pathogen, making it super weak. It can still replicate a tiny bit, but not enough to make you sick. On the other hand, you have inactivated vaccines. Here, they grow the pathogen and then just kill it completely, usually with a chemical like formaldehyde, so there's zero chance it can replicate. So check out how neatly this fits into our universal blueprint. You grow the virus, you harvest it, you purify it, all the steps we talked about, but then you add one very important unique step. The one highlighted right there, inactivation. This is the key moment where the threat gets neutralized, making it safe before it moves on to the final formulation. But science never stands still. Over time, scientists started to wonder, do we really need to show the immune system the entire enemy? This led to a whole new generation of smarter, more targeted vaccine recipes. And this was a massive leap forward. The new idea was, why not isolate just one specific recognizable part of the pathogen, the antigen, and show only that to the immune system? Think of it this way. Instead of introducing the whole soldier, you just show your immune system their uniform. It still learns to recognize the enemy, but in a much safer way. This whole key piece approach gives us a bunch of new strategies. There are subunit vaccines, which use just a single purified protein. Then you have toxoid vaccines, which take a harmful toxin that some bacteria make and render it harmless. And then there are virus-like particles, or VLPs. These are really cool. They're just the empty protein shell of a virus. It looks exactly like the real thing on the outside, but it's totally empty and harmless on the inside. So here's our blueprint again, this time for a toxoid vaccine. You grow the bacteria, harvest the toxin it's making, and purify it. But the unique step here is detoxification. This involves treating the toxin with formaldehyde, and this part isn't quick. It can often take several weeks just to make sure that toxin is completely safe before it's ready to be formulated. And speaking of making things safe, the standards for purity are just mind-boggling. Global regulators like the WHO say a single dose of a vaccine can have no more than 10 nanograms of DNA from the cells used to make it. To give you some perspective, that's a weight so small it's almost impossible to imagine. About what 1,000 of your own cells would weigh. The level of precision required is just incredible. Okay, we've seen the classics, we've seen the smarter recipes. Now we're getting to the most modern chapter in our recipe book. And this one is a genuine revolution that completely changes the game. Here is where everything flips on its head. Instead of spending months manufacturing the antigen, that uniform, in a giant factory and then injecting it into you, these new vaccines just give your body the genetic instructions. That's right, they deliver a recipe, and your own cells read it and become these tiny temporary vaccine factories, producing the antigen themselves. It's amazing. And there are two main ways they do this. First, you have viral vector vaccines. They use a totally harmless virus, think of it as a delivery truck, to carry the genetic recipe into our cells. Then you have mRNA vaccines. These use a tiny, fragile piece of genetic code called messenger RNA that's wrapped up in a protective bubble of SAT so it can get delivered safely.
Let's just focus on that mRNA approach for a second, because it's so wild. It's basically like sending a self-destructing email to your cells. The cell gets the email, follows the recipe to cook up the antigen for the immune system to see, and then the recipe itself, the mRNA, just gets deleted by the cell within a few hours. And let's be super clear, it never goes into the cell's main office, the nucleus. It never, ever touches your DNA. Because of this, the whole manufacturing pipeline looks totally different. The huge innovation here is that it's a completely cell-free process. You don't have to grow any viruses or bacteria at all. First, you create a DNA template. Then, you use enzymes to copy that template into mRNA. And finally, you package that delicate mRNA into its little lipid bubble. Honestly, it's more like chemistry than it is like traditional biology. And no matter how futuristic and high-tech this stuff gets, one thing is always a constant, just absolute rigorous quality control. Every single step from the very first raw materials all the way to filling the final vials is watched over by teams of experts. This constant oversight is the absolute backbone of the whole process. It's what guarantees every single dose is safe and works the way it's supposed to. So, wow, we've gone on quite a journey, huh? From using a whole killed virus all the way to just sending a genetic email. So what's the big takeaway from all this incredible innovation? This table really sums it all up perfectly. The classic inactivated vaccine, you're injecting a killed virus made with old school, reliable tech. The newer subunit vaccines, you're injecting just a single protein, which makes them super pure and safe. But then you have the revolutionary mRNA vaccines. You're injecting genetic instructions made with a super fast, cell-free process. And that gives them one massive advantage: speed. This quote really just nails it. It says, "These new platforms decouple antigen design from traditional pathogen culture." Okay, so what does that actually mean in plain English? It means you don't have to spend months or years trying to figure out how to safely grow a dangerous new virus in a lab. All you need is its genetic code. You can just plug that code into your existing template and go. This is what they call rapid retargeting. And that leaves us with a really, truly exciting question. With these new genetic recipes that we can redesign and adapt almost instantly, the ability to create a new vaccine candidate is faster than it has ever been in human history. It just makes you wonder, what's next? What other diseases, what other huge medical challenges could we finally solve with this technology?